Here I'm going to go through Isaac Physics question B5.7. I've sketched out the diagram that we're given in the question. They tell us this angle is 30 degrees. I'm going to read through the question, and the first thing I'm going to be doing is annotating the diagram with all the information that I'm provided, and then I'm going to be identifying all the values that I have, what equations I might use, come up with a plan, and then solve it. So first of all, information. It says the pub sign shown above is supported by a hinge and by a metal rod. So I'm going to assume that this is my sign, this is my hinge, this is my metal rod. It's good to annotate this stuff because it checks that you actually understand what's going on in the question. If you think, well, where's the metal rod? Then you've not quite understood something. They then tell us to take G is equal to 9.8. So I'm going to put this in our values column. They say calculate the tension in the rod, T, and they say that the sign is 80 centimeters. I'm going to write that as 0.8 meters because I like using the SI units, generally a good idea. Going to label this distance here as 0.8 as well. Okay, what else? They tell us its mass is 30 kilograms. We might need that. I'm going to want to draw the center of mass on here. Now I want to assume it's in the middle, and it says assume that the mass is evenly distributed. So yeah, we're going to put it here because it's a evenly distributed thing, and that's along the axis of symmetry. So I'm going to draw my weight down here, label it 30G, and then I'm going to draw the line of action of my weight force up here. And that now allows me to label some extra distances. So I'm going to label on, again, out of the way, this distance here is 0.4, this distance here is 0.4. So that's the distance between the line of action of the weight and the pivot, or the perpendicular distance between them, and then the line of action of the weight and this point where the tension force is being applied. And it tells us there's no moments about here. They say this is well oiled, or rather it doesn't produce a moment, and the rod is light, and we want to find what T is. So I can easily tell that this is a moments question because we've been given some distances. We've been given something which obviously looks like a pivot, and we've been given some forces, so it has to be moments. So in our equation column, I'm going to be going for the sum of clockwise moments equals the sum of anti-clockwise moments. Now, I'm going to want to decide where I want to take moments about. So I'm going to call this point here A. I'm going to call this point here B, and this point here C. Now, I could pick any of these points to take moments about. I'm going to choose A because that will give me the correct answer in one equation, whereas others won't. So I'll tell you why. We've labeled on the force due to the Earth pulling the sign down. We've labeled on the tension force, but there will also be a third force here, a reaction force from the hinge acting on the sign. And we don't know anything about this force other than we can work out its direction, but I'm not going to go into that in this problem. I mean, in general, it's going to be when you've got these three forces, we've got one down, one up to the left, the other one kind of has to be up to the right to sort of, balance everything. So we don't know much about R, and we don't want to know anything about R. So if we choose A as our pivot, then the moment caused by R becomes 0, and we can leave it out of the question. So that's exactly what we're going to do. We're going to do moments about A that are clockwise equals the sum of the moments about A that are anti-clockwise. So let's go to the next step. Clockwise moments is going to be, this one's quite easy, 30G times 0.4. Now the anti-clockwise moments is a little bit harder. What we want is the anticlockwise moments caused by t about a. If you go back to the definition of a moment, it's the force times the perpendicular distance between the pivot and the line of action of the force. So the line of action of this tension is along here. The perpendicular distance kind of accidentally looks like it goes along the same thing as r, but that's just a coincidence with how I've drawn r. It's this distance here that we want. I'm going to label it d. And actually, we should be not drawing it in the diagram precisely because it causes a mess. So I should be drawing it off to the side, maybe a bit further off to the side, actually. So we want to find out what d is now. Rather than make a mess on this diagram, I'm going to redraw the situation. You can see we've got a triangle there. So I'm going to redraw the triangle out of the way. Looks like this. We know that this length is 0.8. We know this is a right angle. We know this is 30. And we want to find out what that is. Well, that's our opposite. This is our hypotenuse. So we want, out of these three, we want that one because we have hypotenuse and opposite. So we go for sine theta equals opposite over hypotenuse. We want the opposite, so we rearrange. Opposite equals sine theta times by hypotenuse, which is equal to 0.8 sine 30, which is equal to sine 30. Which I think is a half, so that would be 0.4. So then we can label that on if we wanted to equals 0.4. And then we're going to, that's an interesting coincidence. This is going to be t equal times 0.4. And then we just rearrange that for t, remembering that g is 9.8. If you haven't seen the other video on the other way of calculating the moment of t, then please do see that other video, and I explain that this method in a bit more detail. I also explain an alternative way of calculating that moment.